My pleasure to introduce the first speaker, Halpin. As you see, he's at Inria, but he was at W3C for a long time, and he can probably tell you stories why he's no longer there. Harry is involved in lots of new projects, like the NextLeap project. You may see a bit more about this, and the Panoramics project. But he will talk about his standardization work on crypto standards for the internet and the web. So please join me in welcoming Harry.
Thanks, everyone. Okay, so just so I understand who the audience is, so how many people here know about the IETF and W3C and the ICANN everything? Okay. How many people here have participated in a working group at either the IETF or W3C? One brag, two, Brian's not happy about it either. How many people here have been to a physical meeting of any of these groups? Okay. Okay. How many people here have implemented or, let's say, used one of the specifications? Like, have you used web crypto? Okay. Okay. How many people have filed a bug or comment on the specification? Okay. So the goal of this talk is to explain what all these standards bodies do, how they procedurally work, some of the more interesting crypto-relevant work that they're doing, and how to understand their process, so that normally what happens, I would say with cryptography researchers, is that they write wonderful papers, and they often have very good attacks. But then this information, either in the case of an attack, they wonder why is the standard so bad? Why has no one worked on it for 10 or 20 years sometimes, yet why is it so widely deployed? And they have trouble engaging the standards body to fix the standard. Another issue that's often encountered is you have a great new protocol that you think, for example, is the best PAKE of all time, and you want that to be a standard. You're like, well, the current work here is not very good, but you don't really know how to engage with the standardization process. And lastly, so we're trying to show you how you could engage and some interesting places to engage. And lastly, we're going to talk about some of the controversies about which are cases, and controversy is very nice because they're places where there's not consensus, and therefore very useful for future research and open research problems. So crypto standards, we all know NIST standards. Most of us use them every day. The real difference between internet and web standards is that they come from the networking community. So the networking community is, unlike NIST and the crypto community, not competition-based. So typically with a NIST competition, like Bars and Serpent and AES, or God knows what's going on with the post-quantum competition right now, very exciting. The NIST, which is part of the US government, says, the National Institute of Standards and Technology says, hey, we're going to run a contest, we're going to take these submissions, we have some criteria, and depending on the criteria, and assuming no one can sort of break these standards via some form of cryptanalysis, we're going to standardize the US government standard, this particular cryptographic primitive or protocol. Then, typically, although not always, these standards are then taken up by other countries. So Europe tends to copy NIST standards. However, I'm going to point out there's a whole wonderful world of national standards which don't copy NIST, which don't have maybe as much analysis, different linguistic cryptographic communities. Then there's recommendations. So typically based on the NIST standardization process, the US government, particularly the NSA, has the Suite B recommendations, where they sort of say, well, these are the parameters, these are algorithms based on all these old recommendations, which you should be using today. NISA doesn't currently have, I think, an up-to-date parameters and recommendations, but if you don't trust the NSA recommendations, Europe has their own recommended algorithm parameters, and this has been adopted and copied with minor tweaks by the IETF, the IRTF crypto algorithm. So essentially, that's the typical process, and a lot of this, even though there are these recommended documents, a lot of the, for example, key size recommendations and algorithm recommendations come by in the form of folk knowledge, things that you learn either in class or from your classmates, from other cryptographers, from Twitter. You'd be surprised how crazy algorithm choice is, particularly in a space like the blockchain world, where people like IOTA have absolutely no compunction to invent their own hash functions. But typically this is what most people who are sane follow. Now, again, the networking world, which is where most of this crypto gets deployed in, is incredibly different because it's not based on competitions. It's based on some form of open and collaborative process. The goal of the open and collaborative process has numerous goals. One goal is wide review. So rather than have a few people review the specs with some government agency in charge of sort of saying, yeah, this is fine or not, the goal is to have as many people as possible, because the internet's a very big place and we want everyone to be happy, to review the spec. This often takes years, which unfortunately often dates the crypto and the spec. But regardless, that's worked quite well for the internet, and it is currently the process being used in crypto specs of these bodies. Maybe the most overlooked reason for standardization is simply easy identification of the spec. So when you say, hey, I'm implementing the spec, unless there is an actual document with a clear defined crypto algorithm, protocol, ideally parameters, it's very hard to figure out what people are actually implementing. So a lot of, for example, for many years people ask, well, why don't we use more digital signatures on the web? We have all these great digital signature algorithms. They're not new, they've been around for years, but very basic issues and minor implementation differences between various web servers in particular prevented fairly widespread work, such as OAuth, which is what you use when you type Facebook Connect or Google Connect and you go back and forth to authorize your account, from using digital signatures properly. So very small differences, including differences involving white space and all sorts of very silly things, would lead to massive interoperability problems in terms of crypto, and this would lead to a sort of weakening of the crypto. So that's why for OAuth, essentially you have a shared secret that's passed around between the servers and the clients. So you need to be able to easily identify spec, and you need to be able to prove some form of interoperability. Having a spec helps interoperability. Finally, and this is often maybe not talked about as much as it should be, there's lots of antitrust issues. So, large company, let's say for example RSA, they sort of say, hey, we're the people who own this standards. If you want to use RSA, for example, the famous PGP wanting to use RSA case, you have to pay us a licensing fee. This often prevents the deployment of crypto. And for large companies, Microsoft, for example, or Google, or IBM, whatever, you want to typically use an open process so that you don't get accused of antitrust violations, which are legal in the United States and also Europe, where you say, okay, a huge company is, for example, sneaking on Chrome and putting in everyone's Android device and not allowing fair and open leverage for Microsoft, Edge, or Mozilla Firefox. So this is what's called antitrust. And then there's the patent issue, right? So crypto has been historically held back, or at least, let's say, very patent-heavy space. Certicom, elliptic curves come to mind, and various bodies, standards bodies, that's slightly different, but we'll go into that, views around patents, but often the goal is to say, well, if we really want wide implementation, interoperability, we have to somehow license these patents in a reasonable manner, or at least be aware of them, so we can make sure that when you implement a standard, you're not going to accidentally get hit by a licensing fee. So historically, open standards bodies are a bit of a mistake. The original goal for the internet was to have it be ran, at least by networking standards, was to be ran by the same people that run your telephone standards. So some body, the ITU, is the body which assigns essentially area code, country codes to phone numbers. They predate the United Nations, but are now kind of semi-part of it. And they developed something which I'm sure over here knows on the OSI stack with all the different layers, the application layer, the link layer, They were also supposed to develop all the networking layers, but that went wrong for various reasons. And then, so the ITU, in order to participate in the ITU, you have to essentially work for a telco or government, be a government representative. You know, various crypto standards bodies also tend to be government ran. And they actually tend to be quite different. So NIST has all the FIPS publications, which are very useful in interoperability and identifying the standard. Japan has its own interesting world of crypto, which I would, you know, tends to sometimes recommend different things. CryptRec. Russia has a whole different plan of crypto, the Ghost standards, which, and Europe, you know, has its own telecommunications body, ETSI, and occasionally things get complicated. Most people in Europe just copy, you know, whatever the United States and NIST is doing, but every once in a while there's some disagreement. NIST, for example, has standardized something people don't really like DES, and so, you know, European cryptographers will say, hey, we're going to have our own symmetric cipher idea, or maybe recently we've seen this kind of repeat with the Caesar competition, and people then say, okay, maybe Europeans should use something else. You know, this goes back and forth. But the most important thing to remember around open standards is that more or less, within reason, it differs a bit in detail, anyone can show up. It doesn't matter what country you are, who you work for, if you're a grad student or not. When I started working in the IETF and W3C, I was a grad student and no one really seemed to recognize or care. In fact, it led me to be hired as an expert by the European Commission, which more than doubled my graduate student salary, which is quite nice. So I highly recommend getting involved in standards bodies, if only to prevent starving to death. But regardless, we're going to go over the three main standards bodies. We're going to briefly talk about ICANN, because this is an important one where there's a lot of important crypto work to be done, but it's not particularly well known. But let's say it's not well known how to engage with it, and that's sort of on purpose. The IETF, which is, I think, probably the most important one for networking protocol standards, and the W3C, which defines the sort of APIs and protocols used in web browsers, more or less. So again, there's been a lot of debate. So internet governance, so again, the ITU was supposed to develop this whole stack, sort of national level consensus, and essentially it all kind of went wrong. Just because it took a long time. And while the ITU process was taking a long time, and there's lots of meetings, the internet as we know it, founded by TCP/IP and the IP address system, started taking off. You know, the European Commission is still not particularly happy about this, therefore there's these large future internet initiatives and this few kind of grumpiness from the ITU occasionally. But essentially at this point, what sort of happened is the attempts to sort of create national level networks and standardize those sort of fell apart, and everyone just sort of adopted the American sort of TCP/IP standards. Although, truth be told, most of the concepts were copied from French people, such as packet switching and data packets copied from Louis Pouzan's Cyclodes network. But regardless, what happened is that you have ICANN, and ICANN is kind of viewed, when most people say internet governance, they kind of ignore the standards, which are the technically interesting part, and they focus on ICANN. And the reason why they focus on ICANN is because ICANN controls something very important, perhaps the most critical part of global infrastructure today, which is the IP address system. Who gets, it's called IANA, who gets what IP address and what countries get what domain. So you have country level domains, and Switzerland.ch, .org, and this is recently expanded to mean whatever you can buy. But ICANN sort of runs all of that via 13 domain name servers. So these 13 domain name servers, I believe 8 or 9, I think 8 are in the United States, is the top level domain name servers. You know, to update the DNS records, there's a whole crypto process that goes on, but essentially it's a government, a non-governmental bureaucratic process, and the only copies are in Japan, Sweden, and Britain. So of course this makes a lot of other countries unhappy, because they really don't see a particular reason to trust the United States or ICANN, who they believe is a sort of shady front group of the United States, and running the entire world's domain name system, because their internets also depend on the domain name system. So there's a lot of debate. This debate led to the creation by the United Nations of an attempt to resolve this. This was what was called the WCIS, the World Summit for Information Society meetings, in Tunis and a few other places in 2000. And these gave birth to something essentially the United States said, well, you know, we really don't want to change ICANN, and it's going to be very hard to make us. If you try to make us, we're going to walk out the room. And by the way, we control the infrastructure anyways. But we should have a place where countries can meet. Maybe it should be the United Nations, but something a little bit nicer or more vague, where countries can do treaties, talk about the internet. And so they created something called the Internet Governance Forum, which essentially is a UN-backed discussion forum, which actually has no binding power and can't really make decisions. But it gives a place for everyone to go to that's not an ICANN meeting to talk about human rights and crypto and cybersecurity. And these meetings are often, I think, actually useful to go to, although not too often, mainly because they tend to be quite sparse on technical expertise. So there'll be these, you know, you'll meet ministers from various countries who often have very, let's say, idiosyncratic ideas around crypto. And you can go there, you can talk to them and convince them not to do terrible things to their own populations. So that's actually quite useful. Europe doesn't really have that much of a problem, but if you want the European equivalent, it's called Eurodig, which is the European Dialogue on Internet Governance. However, the real power in DNS governance isn't ICANN, and as we know, DNS via DNS bind just maps strings to IP addresses, and it historically comes about because essentially one guy, this is the sort of stereotype of internet governance, old guys with beards, one guy with a beard ran it more or less by himself because he was a very nice guy. This is John Postel. And you know, the internet was essentially, remember, created as a research network between universities, and therefore everything's done in plain text and nothing's authenticated. So it's just kind of crazy if you think about it. So, but at the time in the 70s, it's kind of viewed as okay. So there's been attempts to upgrade DNS to use crypto, and it needs didn't really work out. So this DNSSEC, which has, you know, not only 128-bit master keys and, you know, all sorts of messiness, but it's generally not supported by registrars, so people tend not to use it. But it's a kind of interesting technology to look at. There's a number of attempts to decentralize DNS. Now, they're really worked out. Although for cryptocurrency experts, the oldest fork of Bitcoin, Namecoin, attempts to do just that. But essentially, the issue of DNS governance is who should own what domain name. So it seems like a company like Google should own Google.com. And usually they buy it really quickly. When you have a company, when you want to do a startup, the first thing you do is you buy the domain name. That being said, that was not the case in Namecoin because no one really knew about it. So a bunch of random people squatted Google.com on Namecoin, which is one of the reasons why it's failed. So while ICANN tries to run some social process to sort of, in a somewhat jurisdictional manner, try to make sure that domain names aren't, they can't really stop domain name squatting, but they can deal with the most egregious cases of it. Recently, there was originally kind of a set number of top-level domains, but now ICANN has decided to become a giant money-making machine by essentially allowing people to buy and create new domain names like .amazon or .xxx being the most controversial, or .me or whatever, by essentially allowing people to have a new process for creating and assigning TLDs via auctioning. So that's quite politically contentious. ICANN meetings are held quarterly throughout the world. They have different subsections. There's a policy meeting, and there's the big meeting, and there's a general membership meeting. Typically, ICANN meetings are, again, all about the domain name system, because the domain name system is viewed as a leverage of power. You can go to them. The technical discussions are often very loose, but if you have some nice attacks on the domain name system, which aren't very hard, I would look at, you know, Daniel Bernstein has the whole DNS curve paper, but there's many relatively straightforward attacks on the domain name system, most of which aren't fixed. It's really useful to try to engage with ICANN. That being said, ICANN is infamously opaque, has a very democratic constitution, talking about inclusiveness. They have meetings in Spain and Africa and all sorts of places, not just the United States. But a large study by some friends of ours at NEO showed that no one had ever successfully got involved with ICANN without being personally mentored by someone who already worked at ICANN. So it's hard, but it's nonetheless, I think, attacks are noticed, and so that could be useful to engage. The IETF, on the other hand, is much easier to engage with, although a little bit more confusing. While ICANN has this large structured process, lots of boards and presidents and chairmen, the IETF has no formal membership, so it's been called, I think in US Congress, a narco-hippie commune. Whenever people discover how it works, they get kind of disturbed. Essentially, it's ran by a process around what's called requests for comments, which start out often as very vague and not necessarily well-formed informational drafts. So more or less anything, including like your last crypto homework assignment. If you invent a new protocol, you can talk to the IETF and you can make an informational draft. It's very hard to stop anyone from making an informational draft. So therefore, when you read IETF standards, you probably shouldn't take informational drafts necessarily too seriously. But eventually there is something called Internet Standard, which is actually quite hard to get to because it involves various levels of approval by more or less the entire planet, and also the Internet Architecture Board. And this request for comments, that means it's a kind of real standard. Essentially, it's ran by mailing list discussion. So there's chairs, also mailing lists. There's some mailing lists don't have chairs. If it's a working group, there's a charter. And essentially, what happens is you want to start something in the IETF, you more or less have to have what's called a bird of a feather meeting at what's one of their quarterly face-to-face meetings. And then there's a charter, and that charter has to be approved by the Internet Architecture Board, and then the working group can start. It's assigned to domains. So there's the application domain, there's also the security domain, and these domains have domain leads, which just try to make sure the working group is functional, is moving forward. And often IETF working groups, because they don't really have expiration dates in the same way that some other groups do, can sort of go on sort of semi-indefinitely. Which they try to stop. And one of the nice things about the IETF is that they do have mandatory security considerations. So if you attack an IETF protocol and you break it, you should email the mailing list of the working group and note that attack in the security considerations document. Now, again, it's a very informal process. It was started, the reason it's informal is it was started by a bunch of grad students. IETF meetings more or less look like that. And even though it's quite old-fashioned, so one thing you'll notice with the IETF is that the documents are all still in ASCII, right, for the most part. And the reason for this is because the IETF believes the web is a short-term application. The internet may not be here in a few years, so let's keep everything in ASCII. That's the safest thing to do. Little known, which we'll talk about a little bit more, the IETF actually has a sister organization, which used to be very important, which now is becoming more important again, called the Internet Research Task Force. So the Internet Engineering Task Force is for standards, things that we deploy, while open research questions should go in the IRTF. And essentially, another thing about the IETF most people don't know is this thing called ISOC. So if you want to go to an IETF meeting, and your PhD advisor won't pay for the trip because it's not really an academic crypto conference, and there's blah, blah, blah. ISOC, which is called the Internet Society, essentially is the bank account and nonprofit behind the IETF. They will pay for people to go, particularly people from non-European, outside the United States, and they have a pretty easy to get into fellowship program. So if anyone's interested in going to an IETF meeting, sort of understand the ambience, maybe make some points about protocols, I highly recommend talking to ISOC about their fellowship program. Now, of course, I mean the thing with the internet is that it just wasn't. There was no use of encryption when it started out, and there's various explanations for this. So VintSurf probably there's two lines of explanation for this I've heard. One is Dave Clark and one is VintSurf. So VintSurf, who designed TCP/IP, said, yeah, I was working with the NSA on the design of a secured version of the internet, but at the time all of the encryption was classified, so I couldn't share it. And Diffie-Hellman was only a few years before this, so it wasn't really working yet in code. If I could have started all over again, I would have introduced strong authentication and cryptography into the internet from the beginning. The countervailing point made by David Clark, who was also kind of there at the beginning. So Dave said, yeah, I knew Vint was doing some stuff with the NSA, but I didn't really know exactly what. That being said, David Clark was against the use of encryption in early internet standards because he said, well, I would just do it the exact same way because encryption is a barrier to adoption, particularly in the 1980s, and so therefore we didn't want encryption in the standards. Regardless, conspiracy, not conspiracy, it took a long time. So more or less every single IETF standard has the first version and then an encrypted version. So TCP/IP going to IPsec. You can see there's also a 14-year gap between the plaintext version rolling out and the non-plaintext version. Telnet to SSH, FTP to SFTP, HTTP to TLS, SMTP to OpenPGP. And you can see, minus the bizarre historical circumstance that HTTP was rolled out without encryption, most of the standards were invented in the 80s, and encryption was bolted on usually in the mid-90s. Okay, so, you know, when the NSA revelations came out, I think Bart's going to talk about this more, but it did more or less freak everyone out that all non-encrypted traffic was actually being sort of possibly passively monitored, and also, so this led to sort of everyone looking at the standards again. There was also a sort of disturbing bit of the standard revelations where the NSA had a budget to infiltrate standards bodies, not very large, but you know, 200, a few hundred K. W3C's annual budget is only like 70K. The IETF's budget's a little bit more, I think. So even though it doesn't seem like very much, this budget was pretty large compared to the whole standards body. And historically, you know, the NSA and the IETF had a quite chummy relationship. They would share, for example, the Crypto Research Forum. Or they joined W3C and looked at the XML DSIG signature. Now, I was working at W3C when the Stone revelations happened. We decided to do I did my own personal little internal audit of where did the NSA act. They clearly paid us some money and joined at some point. What standards they interfere with? And it seemed like they joined as soon as W3C started XML DSIG, but they didn't seem to send any emails to any mailing list or interact in any obvious way. Maybe they were just watching. Regardless, this led to sort of wave, depending on how you feel about it, consternation, paranoia, anger. And regardless, one of the nice side effects of this was that people started taking crypto quite seriously at standards bodies. So at W3C, it had been a sort of marginal XML enterprise thing with digital signatures and XML documents. You know, inside of the IETF, most of the crypto hadn't been heavily inspected for 10 years. And in the 90s, people, you know, the state of the art was very different. And to be honest, a lot of the sort of protocol rollout was done by hobbyists, amateurs, occasionally not very much interaction with the academic community. So lots of broken protocols. So it was sort of nice as this led to everyone going through all the old protocols and also making some guidelines for new protocols. So the pervasive monitoring is the TAC RFC basically sort of said, hey, you know, we need to basically minimize the amount of plain text in all of our protocols, so they still aren't really minimizing the amount of identifiers in terms of privacy. They needed to start looking at reversing the traditional flow from NIST, NSA into standards bodies and looking at maybe the community, although they haven't been quite successful in this, should start making their own protocols and primitives and pushing them upwards. There is a giant elliptic curve discussion, which we'll go into. There was discussion about adding human rights considerations to protocols, which we'll go into. And perhaps most importantly, there was fixing TLS. So we're going to start with CFRG. So CFRG, if you're going to subscribe to one mailing list, I mean, the amount of excitement on the mailing list goes up and down. And it can also be mildly traumatizing if you're seriously backing a proposal. But the Crypto Forum Research Group is probably the most interesting IRTF task force. So it was originally supposed to be a sort of, kind of, I would say, loosey-goosey place where academics kind of just commented on new primitives and protocols, and because it wasn't really expected that the NIST primitives and protocols were going to change anytime soon, it wasn't exactly considered a high-action place to be, and so there wasn't actually that many people on it. You know, you would see Dan Brown pushing the Certicom stuff, a few other people, but it wasn't particularly exciting. However, after the Stone revelations, it became very exciting. Primarily due to accusations that the NIST curves were subverted, or hey, at least we should upgrade them. But regardless, it started to attempt to produce RFCs to define new primitives. So Dragon comes to mind, a lot of sort of new sort of various protocols and primitives were going to attempt to be defined in this body, and then they could be spread to different networking level standards. And the procedure for CFRG is a little bit confusing, even to those involved, so I'm just going to comment. Somewhat unusually, it's chaired by Kenny Patterson and Alexei Melkinov. So Kenny, probably most of you know from Royal Holloway. And it, again, like the IETF, it's rough consensus and running code. There isn't a strict consensus process. There's not really strict rules. and ultimately, all decisions are made by the chairs. So the chairs kind of can ask for consensus, can try to address consensus, but ultimately, if you think Dragon's a good thing, or you think there should be a new elliptic curve or not, you have to really convince the two chairs, who are elected because they're kind of nice and fair people. Now, of course, this all came to sort of fruition, and I think Brian will have a lot to say here with this giant determination to sort of have new curves from to replace the NIST P256 elliptic curve standards for Diffie-Hellman and for digital signatures. And you know, there's various reasons for this. So Daniel Bernstein would sort of say, well, look, I believe they're subverted. Most people say a lot of people say, well, that would be alien technology. That's not true. However, they're kind of slow, so we probably should upgrade them anyways, because we know a lot more about designing high-speed elliptic curves now than we did back then. But why should we trust it, and what kind of curves, and what kind of security levels do we want, and should we have one curve, or 3 curves, or 10 curves, or the twisted, the Microsoft proposal to allow people to choose their own base. So anyways, regardless, it became a huge debate and went on for a very long time. It made the mailing list very exciting. Essentially, at the end of it, we did get a minor variation of curve 25519, this X25519, approved for Diffie-Hellman and NDSA, and we have the Mike Hamburg's sort of 448 security level curve as well thrown in there, even though it's not clear if anyone really uses it. But regardless, eventually it sort of worked out, and a lot of IETF standards did start upgrading to using these new, faster elliptic curve primitives. So this is going to be a very exciting place to be in the future, because whatever happens in the NIST post-quantum competition will be reflected in CFRG, and it's going to be huge debates, and I'm sure they're going to be super fun. And it's a good. And if you didn't get your NIST submission, and you don't really know how to interact in NIST submission, you don't really want to fly back and forth to Gaithersburg, this is a great mailing list to be on. However, there's also been some less controversial success stories. So SSL was Secure Sockets Layer, put together by Netscape in 1995. So I think, as Moxie Marlinspike noticed, that it was a bit of a mess. And the reason it was a bit of a mess is because it was sort of bolted on very quickly in order to enable e-commerce. So the same key was used for backing and for encryption, and the handshake wasn't protected, so you could man the middle attacks. And it was sort of generally a mess, and there was many different versions trying to fix all of this mess. And the guy at Netscape was like, yeah, I just kind of made it up really quickly and put it together, but we had to do something. But regardless, eventually a standard came out of it, TLS, which is Transport Layer Security, and it was around for quite a long time without too many people looking at it. But over the last five years, a number of academics have more or less made their very significant careers and published truly wonderful papers by attacking TLS. So this is, by the way, a recipe that can be repeated by any graduate students there. A great way to write a really well-known paper as a graduate student is to look at a protocol, ideally made in the 90s, if not early 2000s, ideally wildly deployed, and then just attack it, because it's probably broken. And TLS 1.2 had a number of kind of epic attacks on it, which I assume most of you have read, or if not, you should read them. They're also very interesting. Crime, Beast, Poodle, some very complex ones, the triple handshake attack, which was kind of hard to get people's head around, and the cipher downgrade attack. So I'm going to mention these two in particular. So the cipher downgrade attack is actually quite easy. So because certain cipher suites were restricted by the United States government for a while, and TLS was made to be compliant with US government restrictions, they allowed easy downgrading. So you can sort of say, actually, maybe I'm not a part, I'm outside the United States, I can't, I'm being connected to from somewhere outside, I want to downgrade to a weaker cipher suite because that's what the rules say. And remarkably, this this algorithm agility was left in TLS unnoticed for a very long time, but not surprised that you can force cipher downgrade attacks and then, of course, break the weak cipher. So that's kind of an interesting generic attack which TLS was open for. Another attack, which Inria was responsible for mostly, is the triple handshake attack, which was much more complicated. It essentially involved tricking the renegotiation process after people had already thought they had fixed it. And the reason why this attack worked is because there was no state machine really defined for TLS. So Inria defined a state machine and used essentially a SAT solver to go through all possible combinations of attacks that could work from that. And with help of Microsoft Research, working on this formal framework called F-star, basically discovered a host of attacks, one of which was a very complex renegotiation attack. Now the great success story of TLS is that rather than say, TLS 1.2 is broken, let's try to patch it, the IETF restarted the working group for TLS 1.3 and actively engages with the academic community, in particular, upgrading the protocol to use both modern crypto primitives and well-defined state machines which have been formally verified. So this is Project Everest from Microsoft. It's pretty interesting in this regard, where it sort of defines formally down both on the primitive level, such as the KDF functions, and on the protocol level, the entire TLS stack, or at least as much of it as possible. The certificate stuff is still quite complicated and unfortunate. Certificate parsing is in general very hard to define rights, done in a sort of chaotic way. But you can sort of see the TLS 1.2 handshake has been, which is quite complicated and therefore has lots of places to be attacked, doesn't really work all that well, has been replaced by a sort of much smoother handshake, much simpler, is formally verified without such wonderful cipher suite problems. And eventually this is going to lead to a whole new spec, still more or less in process. And this is a good way to read an IETF spec. It's more or less done, but you can sort of see there's different versions. The RFC with the number on it is the most important version. The earliest version is 00. The latest version is the highest integer, which in this case is 23. You can sort of see it updates previous RFCs. It's standards track. It's not informational draft, so take it seriously. They have an expiration date, so if it is not continually upgraded, the IETF will kill it after the expiration date. It often just kind of hangs out on the internet. People don't really notice the expiration date. So if you're attacking an IETF protocol, make sure you really find the latest versions, otherwise you're going to look quite silly. And you can also make sure that there's no new protocol which obsoletes your RFCs. So RFCs formally obsolete other RFCs, so you shouldn't use them, and you can sort of see TLS 1.3 is updating previous TLS specs and obsoleting a number of older specs. And that's kind of what they look like. And it's quite useful. A lot of people don't know about these features, but they're just up there. If you have some questions about a particular spec, and you use RFC Editor, you can actually quite easily email the working group, look at the bug tracker, even view it as a PDF or HTML for easier printing, and look at the diffs. So the diffs are the perhaps, this is, if you're really trying to figure out what a working group's doing, the simplest way is to go to the working group, don't bother to read all the email archives, that will take forever. Just go through the big diffs. Just fly through the diffs and you'll sort of see where things are changing and where they aren't. And one of the other interesting things that come out of the IETF is the Human Rights Protocol Consideration Working Group, which basically sort of said, well, one of the great concerns of the IETF and ICANN is that Russia and China and other countries will break away because the NSA and NIST are acting in dodgy manners and form their own standards body and their own separate internets. And at the same point, there's been a lot of discussion over TLS about, we want to optimize network traffic, so maybe we should be able to break this encryption and optimize some things in some middle boxes. This led to huge debates on TLS working group mailing lists. And one of the ways to possibly fix this, being backed by at least rather remarkably some of the IAB, is to build not only security considerations in the protocol, but human rights considerations in the protocol. So you have user rights, consumer protection, blah, blah, blah. You have architectural principles, and you have all these things which everyone talks about all the time: interoperability, end-to-end principle, resiliency, transparency, graceful degradation, data minimization, innovation at the edges. But none of these terms are really well defined. Everyone has a sort of intuitive understanding to them, and it's not really understood how they possibly might map or might not map to human rights. So this giant research task force is trying to figure this out. It's kind of interesting if you're interested in the more policy-driven aspects. I think the goal for the working group is probably to have some sort of human rights review for new protocols, and we'll see how that goes. Of course, there are considerable pushback to this working group. Although that being said, standards are quite useful. So for example, after the NSA revelations, there was a massive decreased amount of Cisco routers being bought. NSA's sort of compromised Cisco, and Huawei's like, hey, you should buy our stuff instead. And people say, why should we trust Huawei? The Chinese government's also just compromising you. And so, weirdly enough, based off work from here and in other working groups around certificate transparency, the American Civil Liberties Union and Huawei got together in the IETF and basically said, well, let's make a way to prove using Merkle trees, with the leaves being binaries of updates, and our software updates the software updates you're getting are the software updates everyone else is getting. So that's the binary transparency effort. So in the IETF meetings, you can often see these sort of interesting pairings as people even people who seem very disparate politically or nationally or even research-wise, try to get together to basically do the best thing, both for themselves and the internet. In fact, one of the great results of the IETF is the World Wide Web. And so the nice thing about the IETF is it's based on what's called open innovation. You don't have to ask anyone. So as Tim said, I just put the World Wide Web together. I didn't have to ask anyone. I just put hypertext on top of TCP/IP, and there it went. So that's kind of great. But one of the problems is that the IETF can be very slow. And so, Tim tried to create an HTTP working group and a URI working group, a URL, Universal Resource Locator, and it just started going really slowly. And a bunch of companies showed up to the IETF, and they said, oh, this is going really slow, why don't we... The web was getting really big, really taking off at the time, and Tim was quite worried that the companies would run off and make their own proprietary version of the web. So you remember, for those of us who are older, that there was best viewed with Microsoft, best viewed with Netscape. There's all these sort of interoperability problems. And so Tim made the World Wide Web Consortium to be a sort of more structured, more formal, and more faster moving version of the IETF for the web. They don't hate each other. They basically get along. It has directed by Tim Berners-Lee. So essentially, there's an advisory board, an advisory council, and it's a consortium. So each member, like a company, for about, I think, $70,000, or a nonprofit or a university for $5,000, pays the World Wide Web Consortium, and they elect a member to the advisory council. They can vote and make decisions. So on some level, much more clear than the IETF. However, Tim Berners-Lee, who is a very nice guy, is ultimately the director and has kind of final decision-making power and everything. Unlike the rest of the IETF, so the IETF, if you really object, the chair can just ignore you and things will just keep going. The World Wide Web Consortium has a formal objection process. You can say, I really object, I formally object, and then the staff is forced to write a response about why they either agree with your objection or why they disagree with it. And so they can't just kind of override you by ignoring you. And at certain points in the W3C process, any comment has to be shown it's been addressed before getting to the next stage of the process. So that's, on some level, W3C has a more mature way of dealing with comments from the peanut gallery. And you have working drafts, which are essentially the same as the sort of early stage informational drafts. And they go to recommendations. Recommendations are the full-fledged, stable W3C standard. It has some advantages over the IETF. So not only is it a sort of more clear process, it uses GitHub, which makes life a bit easier. And in the IETF for Internet Standards, there's not really a clear way, there's not a clear test suite. You're not forced to test your standards before saying they're a standard to make sure there's interoperability. The W3C requires for every feature in a standard that there be interoperability testing, so that there be sort of two tests, two implementations, each can prove that they have implemented this correctly and in an interoperable manner. Now W3C sort of slacking a bit on HTML, and so a lot of HTML, the new versions, are being ran by this thing called WHATWG, the Web Hypertext Application Technology Working Group, which has a more IETF way of working, a bit more loose, a bit more, I would say, dictatorship by a few people, but much faster. And that's been a sort of point of contention. So, the other point about the W3C is that it has unlike the IETF is often accusations that people are secretly working for companies, or they're secret agents, or they're working for the NSA, or they're on the NSA's payroll. So there's a lot of, one thing the W3C sort of says is, well, in order to make sure our process is fair, each working group will have a neutral paid staff member whose job is to just basically keep things neutral, keep things running, and they're paid by the membership fees. And working groups have a clear start and end date, so if they don't accomplish their goals, they can be shut down. And so essentially, this is a W3C process in a little bit more detail. You start with a charter. The charter is developed by the staff. It's a little bit, that's probably the point where the W3C staff exert the most power after an open workshop. So usually an open workshop's called for, and anyone, including non-W3C members, come up and say, I think the web needs this. So the open workshop can say, hey, I think the web needs a crypto API. So the web crypto API came out of a desire by people to do digital signatures, which was just put forward by Jeff Hodges from PayPal, kind of out of the blue at a workshop that was more focused on identity standards. But it ended up being a good idea, so we decided to do it. We made a charter. The charter has the goals, the standards that are going to be produced, and it produces, there's a call to join, there's working drafts. They become last call working drafts. So at that point, you really shouldn't edit them very much. And then they become what's called candidate recommendations. The candidate recommendations then have to prove interoperability. They become proposed recommendations, and then finally recommendations. Now, where should you get involved in? Well, you want to get involved early. Not very fun getting involved late, unless you have some sort of epic attack on the system. To get involved early, you can see if your university or company is a W3C member. But if they're not, you can become what's called an invited expert. So an invited expert is anyone that can demonstrate expertise in the subject. So ideally not random people off the internet, but ideally someone with a degree or some background in industry, which most people, including PhD students, would count as. So in order to become an invited expert, you just email the chairs of the W3C staff of the working group and you ask, and they will ask you for a resume. And then you give them your resume and say, yeah, you should join, then you can jump on. Also, most working groups, if that's too much work for you, have a public mailing list for comments, the public GitHub for comments. You can just make your comments there as well. Now, why is the W3C more formal? It's more formal because there's more patent protections. So the IETF has an older, more loosey-goosey patent policy called the IETF Note Well. So the IETF Note Well simply says, if there's a patent and you know about it, you should tell us about it. And this, of course, a lot of companies have rules around knowing or not knowing about patents. So you enter bizarre world conversations on IETF mailing list where someone says, hey, I have a patent, and says, oh, I haven't read that email, I can't look at it, and then everything goes a bit crazy, and this sometimes disrupts the standardization process. W3C said that was kind of crazy. Let's have a royalty-free patent policy. Royalty-free doesn't mean that you give up your patents. It just means that you agree to license them royalty-free to anyone who implements the spec. Okay, and that's pretty important, and we'll go a little bit back into that in more detail. So what's something that W3C has done? So TLS is a great way to set up a secure channel. We use it every day. The W3C, maybe can it do something as high impact? Well, currently, the plan is to kill passwords, right? So passwords they can be reused, this leads to phishing, they can be intercepted. We still use them a lot. And how many people here have YubiKeys or have used a hardware key? Okay, so, or do you use your phone to log in with NFC? Anyone do that yet? Okay, only Bart. Anyways, regardless, it can be done. And essentially, one of the wonderful things about W3C is all these companies who normally sometimes may disagree due to business reasons, such as Microsoft, Mozilla, Google, PayPal, all got together based on work from the FIDO Alliance, the Fast Identity Online Alliance, a kind of closed industry consortium. It said, hey, we're going to actually get rid of passwords because passwords are such a large security threat. So what you do is, you establish a TLS connection, ideally using TLS 1.3 as normal. And then you send a promise up to the server. The server uses sort of challenge response protocol. The server sends you a challenge, the nonce attached. You say, hey, I'm a user. That's your nonce. I'm going to sign this with a key. These keys are generated per origin, so they can't be linked across origins for better privacy. The domain is attached, and there's also a way, so to prevent man-in-the-middle attacks, to sort of say that there's identify a TLS connection called the TLS connection state, and then you basically take your phone or USB or whatever hardware key, and you send this sort of signed response back to the server that sent you the challenge. And so that if there are any attacks, they can be generally detected. Again, it's very important. The web has as its primary security model the same origin policy, which is just that stuff from one origin, or more or less domain, google.com, should be accessible via another domain, such as facebook.com. And so therefore, you'd have different keys for different origins. So there's not one big master key to rule them all. And so what appears to be a single key, secret key on a, for example, so like a YubiKey is actually, deriving lots and lots of different keys per origin. And that by putting all of the stuff in, it's phishing resistant. And man-in-the-middle resistant, because the TLS connection, if it's broken and restarted, not only the origin prevents phishing, but the state of the TLS connection will be changed if the connection was restarted, and this makes it man-in-the-middle resistant. So this is a pretty good design. It's not really super widely implemented, but it should be in everyone's browser sometime this year. You can sort of see, this is what W3C recommendation looks like. You have the latest version, and you have the editors. Then you can sort of see it's a pretty large collection of folks from across industry. So it's clear, the W3C can kill passwords. This would be a huge deal, and would improve everyone's security for the better. That being said, using crypto on the web and JavaScript, is also sort of dangerous. So the thing I was working on before web authentication, W3C, was the Web Crypto API, which Brian and other folks also worked on. Started in 2012, finished in 2016. Primarily led by the editor from Netflix and Ryan Slevy from Google, who stepped down. And so if you're ever building crypto in JavaScript, there's lots of libraries out there. There's Dan Bonet's Stanford library. There's the JavaScript versions of Sodium. But regardless, if you want to access the same primitives that are being used in the TLS library of the browser, you generally want to use the Web Crypto API. And we invented this because we noticed that lots of people were more or less rolling their own crypto in JavaScript. This was broken, wasn't constant time, lots of side channel attacks, all sorts of stuff. And including very basic things such as you couldn't generate random numbers in JavaScript properly. So again, W3C fixed all this. We have strong pseudo-random number generation. Key storage is not particularly secure. It's in local storage. So it depends how you feel about local storage. I'm going to put very important keys there. But you do get RSA, ECDH, hash functions. You get a lot of nice stuff. KDF, PBE KDF. But the main thing which the web doesn't change is that it's still JavaScript ran from the server on the client, so you still have this trusted server model. And some people try to get around this via key wrapping, but we at Inria did a formal analysis of the API and then tested it, and indeed the key wrapping can be quite trivially broken by the server. So this is all good. W3C does a lot of great things. But one of the most interesting parts of W3C, which isn't particularly well understood, is how it clears out patents from standards. So the US patent system is pretty liberal or pretty terrible. It doesn't really matter who invented something, it matters who's the first to file it. And even if you're outside the United States, it's very hard to escape the United States patent system because it globally harmonizes via the UN, the WIPO, WTO WIPO process. So even if you think, so generally when you're a company, you generally file in the United States and you try to harmonize to cover world countries which have actual functional patent systems, such as Europe. W3C got hit by patent claims by Drummond Reed, who's now currently working on blockchain stuff. So one of the warnings I'll point about blockchain stuff is the blockchain stuff is a pile of patents, including patents made by people who have a long history of being patent trolling scumbags like Drummond Reed, and I think working on Sovereign, I think. So this is a patent claim on the web back in like '92 by Intermind or something. So anyways, regardless, lots of sketchy patents out there. If you really think your thing should be globally usable infrastructure, you want to get rid of them. Blockchain companies typically don't worry about this now. The web didn't either, but then the web had developed this whole process to get rid of them. And the way that W3C did it is quite clever. It says, when a working group starts, you commit your patents on the charter, and then when the recommendations finalize, the text is set in stone, so to speak, you reset your patent obligations to the final recommendation. Now, this is quite interesting because essentially it creates a sort of, not really a patent war chest. It's better thought of maybe as a balance of terror. Because if a patent troll or company inside W3C decides that they will go after patents, they will say, actually, I have a patent on HTML, I have a patent on web crypto, whatever, you then lose the rights. The offending patent troll then loses the royalty-free licensing rights on all of the patents in the pool, which are quite huge now because they encompass HTML, XML, all sorts of things, lots of IBM patents in there. So you will almost definitely lose any patent battle. So that's actually quite clever patent policy, probably much more clever than the IETF. And it's worked fairly well. There's been very limited number of violations from patent trolls and no violations by member companies. However, this led to the DRM debate being reinstigated. So, for a long time, companies have wanted DRM. In fact, one of the first W3C workshops back in 2001 was, how do we put DRM on the web? And at the time, the problem, DRM, even compared to normal crypto, because lots of money is involved, is very heavily patented. So there's sort of 5 large patent pools, they all hate each other, none of them really get along. So you couldn't standardize DRM. However, with the rise of Netflix and streaming video, there was a desire by companies to basically fix the DRM situation, to have a sort of DRM built into the browser. The main reason, which is a pretty good reason, is that downloading third-party plugins, particularly Adobe plugins for Flash, which had DRM built in, were very dangerous. These third-party plugins broke the same origin policy, could access whatever data anywhere in the browser, regardless of the origin, and often had security flaws. So they said, well, if we just built in a DRM standard into the browser, this would be great, and we wouldn't have to install plugins. And the way you get around all the DRM patents, you sort of say, well, we're not going to actually standardize the thing that does DRM, the thing which decrypts the video. We're going to standardize a JavaScript shim to this thing which does the decryption, which is called the content decryption module. Now this led to a huge fight because obviously DRM, at least in the United States, has a sort of very nasty legal set of laws behind it called the DMCA. And these DMCAs, most security researchers basically think it's security by obscurity, and it prevents them from auditing DRM systems. So basically, it puts a black box in your machine, and this is dangerous. We won't be able to audit it. So EFF, the Electronic Freedom Frontier Foundation, want a protection for security researchers on DRM. Anyways, so how did it happen? So W3C has this really formal process. So you think that something like DRM would have been noticed really early on. However, because of this mess with WhatWG over HTML, then there are 2 versions of HTML. There's a W3C version, a bit dated, and the WhatWG version, a bit without as much process, but more up to date. And when W3C said, yeah, we're going to give up on XHTML, we're going to just copy the WhatWG's version, they made what's called HTML5 in 2007. And this, they said, well, how can we be fast and lightweight while still having this big process? Well, we're going to invent something called HTML extensions. So this allows, without going through a whole giant rechartering, all these votes, and all this other nonsense, we're going to just let people add stuff to HTML via an extension process. And so Netflix, quite cleverly, and this is unique inside W3C, discovered the extension process and proposed in 2012, basically no one noticing, encrypted media extensions. And so this is how, encrypted media extensions work. I'm going to go through this really quickly, but it's all in the spec. Essentially, you know, I want to watch a Netflix movie, but it has a license. This license is maintained by a licensed server. This licensed server may not be the same as the web server. So, for example, you know, Netflix may not really care if you have a license or not, but they need to make sure that their legal obligations with the various Hollywood companies, NPA or all, and RIAA, are all legally well defined, and they're not breaking any laws by allowing this movie on Netflix. So there's a license server. This license server has the license information. So when you're getting a stream of video, it's buffered and it's encrypted, you need a key to decrypt it, and you basically ask the website gets, you know, checks for the license server. Then, if you've paid for it or are otherwise entitled to have that key, it opens what's called a media key session, which just sends a bunch of messages around, because it's sort of a symmetric cipher, so things are encrypted in blocks. You have to renew the key and refresh it every so often, and this is then, once you've proven that you indeed do have the right license, the video is then sent to the content decryption module, which is not usually, although it can be downloaded, usually stored natively in the browser or even in the operating system level. And that content decryption module decrypts the video and frame by frame and passes it back up. We can go into that in more detail, but regardless, yeah. Yeah.
Application, where does it run?
So this is a web application.
It's on the web.
It's on the web, yeah. So this is a web application being ran by a web server, which has access to a license server, and so the idea is that we can run Netflix in the browser and don't have to install it. Content decryption modules are kind of where the action is, and everyone has them now. Google has Google Widevine. This is the quote-unquote open source DRM, CDM. Microsoft, if you have Microsoft, comes with PlayReady. The one that everyone used to install, which used to be used by Mozilla, but which is now Mozilla's replacing with Google Widevine, is Adobe Primetime. So, and so that this is totally unreadable, but regardless, you can basically run a whole bunch of complicated JavaScript and decrypt encrypted media using this API. And it's not, this seems really terrible, but then compared to installing a plugin, it's actually readable. You can figure out what version, you know, what sort of bit of this code goes to what bits of the spec, and it has lots of advantages. So, for example, it's asynchronous, so if things take a long time to decrypt, it doesn't prevent you from doing other things in the web page. Now, this led to this huge debate because evidently one of the great fears is that so the W3C was sort of like, well, if we standardize DRM, we get rid of these Adobe plugins, that's great, there's less security flaws, wonderful. However, one of the concerns is, well, you know, DRM died on iTunes and in terms of music because it was kind of hard to use and hard to use in an interoperable manner. If we do have this wonderful interoperable standard for DRM, it's going to be used in more and more places, and it's going to spread. And in fact, it did when people started working on the standard. Unless you run Linux, let's say you say, I don't want DRM on my computer, I only use Firefox. In a silent upgrade, you know, Firefox essentially installed DRM on all Mozilla users, non-Linux users at least, machines, without any kind of user consent or even users noticing. So on that level, the amount of DRM systems which previously required you to kind of click a button and hit install for a plugin or buy an operating system which had DRM already baked in already, was kind of increased. It became increasingly hard not to use DRM on the web, if not impossible. You can still use some browsers that don't have it, Brave for example. But regardless, EFF said, well, you know, there's just going to be more and more DRM on the web, so let's try to figure out a way to protect security researchers. So basically, EFF tried to copy W3C's patent policy. They sort of said, well, if you try to bring a lawsuit under the DMCA, against any person of any jurisdiction that regulates the circumvention of technological measures, then you're breaking this covenant. And all W3C companies, in order for us to standardize DRM, should sign this covenant to protect security researchers. And various countries have different laws around this. But regardless, it seemed like generally, for the crypto research community, it seemed to be a generally pretty good compromise. It didn't prevent the EME from going forward, because everyone did agree the plugin situation was pretty terrible, but it provided an additional layer of protection from researchers, because there's actually only so many CDMs. If each of the CDM manufacturers agreed to this, this would allow people to, for example, write an academic paper breaking a DRM system and publish it. And this has already happened. Google Widevine was already broken, and people could decrypt it, but it was broken by researchers in Israel, and Israel is one of the few countries that has no relation, doesn't sign the DMCA, has very loose laws in this regard. So regardless, a bunch of security researchers, everyone from Ron Rivest to bunches of other people, some of who are here, Tanya Long, Bruce Schneier, Steve Murdoch, a bunch of, about 200 or some researchers agreed that this was a good idea. And then when the working group decided that they were going to actually finish the standardization process in 2016, EFF said, well, you really have to sign this petition, otherwise we're formally objecting. Now regardless, it was already implemented in all major browsers and installed, Microsoft and Google in 2014, but this huge fight happened in 2016, and due to the amount of media pressure the EFF put on W3C, there was even letters from JustNet Coalition, some global South body, saying, hey, it's digital colonialism if you install DRM on our users' machines without their consent. UNESCO said, you got to be careful DRM if you don't do it right. Could be this. Could also have a dual purpose of surveillance and censorship. You can see there was accusations that the working group was controlled by DRM vendors. We actually did some quantitative analysis of this, and the DRM lobby, which is the actual copyright holder, is actually a very small percentage, and most of the working group was browser vendors, but there was a pretty large representation of civil society. Actually very little interaction from W3C, and very little interaction from invited experts. But regardless, it's definitely true that the companies and the browsers are the majority of the working group, but there was a fair amount of civil society representation. And that being said, the activity was mainly done by the browsers and the DRM vendors. With civil society, mostly represented by a single person, Cory Doctorow, sending about 60 emails out, while everyone else sent more like 200 or so. And the mailing and how this kind of played out is in practice, as the DRM debate started, that civil society would basically there'd be lots of debates, but these debates would come only at certain steps in the formal process where EFF felt they could put a wrench in the process and try to pull leverage to get the W3C members to sign the security petition. And then you'll see that there essentially was large periods where in between these sort of moments with civil society heavily engaged, the rest of the working group, mostly browsers and DRM vendors and a few other people, just kind of went along and solved bugs and fixed the spec up. But this pressure got pretty high. It led to protests, the first time ever. You've probably seen a street protest at a standards meeting. So lots of people anonymous mass showed up, crashed the dinner parties, screwed up Tim Berners-Lee's dinner. There were street protests in Cambridge and MIT over standards, lots of back and forth. I said, well, I thought this security petition was not perfect and should be sent to everyone's lawyers because I didn't really trust the EFF lawyers to actually get the text right, but I felt it was going in the right direction, should be seriously considered. And when it wasn't, I quit W3C, just fine. I just got a job at Inria because I obviously didn't want to be involved in a body that wasn't actually actively trying to work on protecting security researchers. That being said, the end game was Tim Berners-Lee finally approved it without the EFF comment in 2017. This led to a recall vote against Tim Berners-Lee, first time in history, where you can sort of see the W3C is actually pretty evenly divided, but the majority supported DRM. 108 supported, 57 against, 20 abstentions, and therefore it went forward as an official recommendation. Nonetheless, this might be a Pyrrhic victory because the WCC, which has been maintaining HTML this whole time, said, well, what did W3C really do? They just added DRM to HTML. DRM is unethical, so, why don't we just keep doing the real work in WCC? And now they seem to be ramping that up by adding a steering group, including Microsoft, and patent commitments. So now the web is more or less even more fractured than it once was, with a W3C version of HTML DRM, which is maybe not as up to date, and a non-DRM version over at WCC, which is a bit more up to date. And now they're both getting steering groups and patent commitments, essentially setting up parallel standards bodies for the web, which, you can sort of see historically why this happened, because there were such large debates and various personal affairs. That being said, the end game is probably detrimental for developers, because developers just want to go to one place to find the standard. If you have two parallel web standards, it's just confusing for everyone. And so people go to one, and why is web crypto on W3C and not on WCC, or what is the right way to decrypt this DRM media? And it's confusing. So you really kind of probably should fix the situation. I don't honestly know how, but I'm up for hearing about it. And again, the arguments are pretty messy, right? There's generally pretty good reasons for getting rid of plugins in terms of DRM, and those reasons are pretty good. That being said, there's often the people in charge who went maybe a bit too far and said, oh, actually, don't worry, sandboxing in the browser is totally secure, so if the DRM goes wrong, it's only, be limited. And that's obviously not true, because sandboxing in the browser is a bit of a catastrophic mess. It prevents JavaScript from being loaded, but everyone sort of shares the same memory space and content processes. It's not like operating system level protection. And everyone also does agree, everyone, including the people that support DRM for the most part, that the DMCA is a giant catastrophe, right? So there's these exceptions for fair use, educational uses, backing up media, parity. These jurisdictional exceptions for fair use just work differently in different jurisdictions. How do you possibly take that into account? So a good example is India. So India agrees that breaking DRM should be illegal, but it's legal to, for example, break DRM and publish as academic paper, because only if you're breaking DRM, which actually breaks the copyright, and you're using tools to break the copyright, is that punishable. Actually, the manufacture and distribution of circumvention tools in India is legal. So not only is it writing a paper legal, but actually putting something like a DRM cracker on the internet would also be legal. So again, lots of different legal differences. How do you take them into account? And there's also some other good points, right? So accessibility, right? So, it's much easier for encrypted media to have, in the W3C version, subtitles, which aren't encrypted, which can be read by, for example, screen readers. That being said, encrypted media still prevents machine learning-based automatic subtitles, which seems to be at least where Apple's going. So it's not 100% clear-cut, but that seems to be a good advantage. But again, back to security, if security by obscurity doesn't really work. There has been work by Microsoft Research in particular, trying to allow researchers to audit DRM and not modify the code. I think Brian can address that. I think he's worked on it quite extensively. It's been up and down in terms of deployment, but there's really good ideas for allowing researchers to audit DRM code, various forms of remote attestation, and it's going to be very tricky with the DMCA in place, without some of this research in place, to sort of test the security of these systems. Privacy, again, is complicated. DRM requires you buying licenses. It kind of requires identifying people, so there's some privacy issues, but it's unclear how to get around them. It's unclear around how to get around, I thought a really good solution might be just having better informed consent while DRM systems being off by default, allowing people to just turn them on when they're aware of them. you know, which would allow, I think would be a nice compromise that's purely technical, but wasn't accepted. So regardless, internet governance needs you to engage. The people who architect standards sort of got the job by historical accident, more or less by virtue of being graduate students around at the right time, at the right place. And that's how the IETF works. But now, you know, the internet's a big deal. It needs to grow up. We need more academic researchers and more companies. And it has to be more global, less American, involving people from all over the world, including China and Russia. So how do we do this properly and in a way which is more democratic, but which doesn't kind of result in nation-state level control of the internet, which would just defeat a lot of the great things we all get from the internet. And there's lots of real debates, as shown by W3C DRM debate, as shown by the TLS work, as shown by controversies around human rights. There's a lot of really thorny issues, and in general, because these open governance bodies are generally voluntary, so companies often pay people to engage with them. Sometimes nonprofits and civil society do. They really, who does the work kind of usually wins. So we need more people who are neutral, who really have the best interest of the internet and cryptography in mind to engage in standards bodies. That being said, if you're used to this process, it's a bit crazy. Crypto designed by committee is maybe not all, doesn't always work out really well. It's kind of funky sometimes. And we still need a way to get around one of the problems we've seen again and again, which is in an open voluntary body. The crypto is often chosen, particularly by a lot of implementers who maybe aren't actually well versed in the academic literature, by human reputation. So, oh, I think Daniel Bernstein's great. Actually, I think he's a jerk. I like this other guy better. You know, Craig Costello's singular misogynies are wonderful because Craig is awesome. And so you often have this issue where people kind of choose their crypto based on who they like rather than rational analysis. And this is probably not the best way to go. At Inria, we believe that this is hard. Provable security of manual proof is good, but it's still a black art to a large extent. A lot of manual skill involved, and there's lots of big problems. So we support formal verification, primarily as shown in TLS 1.3, but also web crypto and now web authentication as the way forward. So we can sort of say, why should you trust this crypto? You should trust this crypto because we have proofs of security that anyone can check for all, including the incredibly boring parts of the protocol. And we can check for functional correctness in all cases. Now that's a big statement, so you always have to say, well, all cases except the certificate parsing, for example, for TLS, but regardless, there's been a lot of progress there. One of the biggest critiques of formal verification is that, well, you're only really verifying a model of the code. So why would, I'm running this crazy C code over here, you have this thing that looks like Prolog over there. How are these, I'm glad you have these formal proofs over there, but not only are you trusting some crazy Microsoft stat solver that's both incomplete and unsound, has soundness completeness issues, but hey, look, I'm running this whole different C code. So one of the things that we've been working at Inria, just a brief moment of advertising before we go to questions, is we've been working on F-star, and F-star is this really nice framework because essentially, no actual relation to C#, but more relation to OCaml, but it lets you basically do formal verification and then compile down using a verified compiler all the way down to CompCert C, which is then C that you can run. And so this has led to, we don't really have this quite working for the computational model proofs, but we can go all the way down to C very soon, JavaScript, and then you can run formally verified code in a real app. Now, it's kind of crazy, like, why would I trust this formally verified code? Isn't it very slow? So formally verified code has a reputation for being terribly slow and inefficient, but we're getting better and better at it. And not only can you do the specs, compile down to C, this C can actually be pretty fast and have good, getting better and better constant time guarantees. And now, if you're using Mozilla, Mozilla finally is replacing their old stuff on NSS with formally verified crypto called Hacklestar from Inria. So there'll be a presentation at this. We have the last presentation by Karthik at Inria in Real World Crypto. We'll cover Hackle Star in detail. But we think this is a really exciting line of research. Both Microsoft and Mozilla, Google, like kind of everyone sort of says, yeah, this is probably better than this sort of trusting random people, or even people we really like with crypto. And the main problem is still a little bit slow. We can't do like per microarchitecture, really fast assembly on it. But hey, you know, why not a formally verified LLVM? We're going to get there eventually. So we're seeing lots of progress in this space. And we do believe that this is probably going to be the future of standardized crypto, where you can't just say, hey, look, I invented a crypto standard, and here's some proofs. Yeah, I kind of thought about them for a while, and maybe or maybe not the reviewer read them in my paper, because reviewers often kind of skip through those if they don't have much time. But instead, we can sort of say, look, here's machine check proofs. You can check them yourself. And by the way, here's a library which carries these proofs. And we think that's absolutely great. And in the long term, we can even eventually do stuff like get rid of OpenSSL, which had a bunch of attacks, and get general purpose crypto libraries. We're currently working on formally verifying. A lot of people kind of upset at standards bodies, kind of slow, so you're seeing stuff like signal and noise being developed without standards. So we've been working on formally verifying signal and noise, and eventually get the speed so we can be as fast, if not faster, than really hard to read, yet really highly optimized assembly that people trust anyways, despite the fact that very few people can read it and check it. So that's what we think the future is. That's it. But summarize, lots of good stuff, lots of bad stuff, a lot of controversies. If you have any questions, we have a little bit of time.
Thank you very much. Questions for Harry?
Not one question?
I have questions, of course.
Okay.
Just as to warm up. So you were kind of dismissive about DNSSEC. I know that like the Netherlands and Sweden have tried to kind of, I think the adoption there is a bit higher. Is it the government's problem, or is it just
the main problem? Okay. DNS. So you say it's high, adoption is higher in Sweden, and
I think it has some impact that the government kind of pushed it.
Okay. Well, it's possible if you're a government, you have lots of resources to do DNSSEC properly. That being said, most websites don't do DNSSEC because domain registrars generally do not support it very well. A lot of the big ones don't support it at all. That's where most people get their domain names, configure their domain name systems, through these crazy web admin panels. And since they don't support it, no one supports it. And then there's all these critiques of it, such as the sort of small key size critiques. So I think there's a lot of work that can be done in DNSSEC. How can we get something like DNSSEC that gets wider deployment? So I wouldn't say it's over. That being said, it took, how long did it take to make DNSSEC? Like 10 years? 15 years? Yeah, it took at least 10 years to finish that standard. And
that was 7 years later, there was no deployment.
Yeah, 7 years later, not being much deployment. So you can either view that as we should just give up and let DNS remain terribly insecure, or you could view it as maybe this should be an interesting research problem that someone could probably fix. Something a little bit more lightweight, which doesn't have so many implementation hooks that require registrar and stuff. So a lot of the problems with a lot of standards is that the standard may look great in theory, but it has a dependency on like a third party, which isn't really in the spec. So with domain name systems, this is the registrars and all the people that control the domain name registries. They weren't really consulted very heavily on DNSSEC spec, so they didn't really care about it when it happened. And same with the certificate authority system. So TLS really depends on certificates being properly trusted. And it ends up, the certificate, these are essentially just a giant list, ran in browsers, a white list. And the groups that run these white lists, the certificate, the browser, CAB, certificate, I forget what the A is. But regardless, these are closed bodies that may not really be checking to see if people are secure. So you have things like the Genodar attack, everything goes a bit crazy. And even the TLS spec is great. If someone can just like get a Google certificate, it doesn't really matter. So these are often important things to think about when you're designing standards. Think about the whole ecosystem. Any other concerns, questions?
I had one concern at the very beginning. Packet switching from France. One of Davis was great.
Ah, yes, the great Britain versus France debate. So I think what happened is that I'm not sure, did Louis Pouzon or Davies do it? I think they did it independently. But I think I think Pouzon talked, they all talked a bit, and I think the Brits decided to hand off the post office, if I remember correctly, which then sort of killed whatever this British net was going to be. They just didn't do anything. Well, the business state was killing it, right? So there's a lot of independent invention. It wasn't all just Americans. Most of the good ideas are actually from Britain and France, like many good ideas, but then copied by Americans and then pushed out really heavily. So Americans are very good at commercial exploitation, maybe not so good at other parts.
So you're optimistic until that's 1.3, so what
Yeah.
about the 0 encrypt stuff?
Okay, that's yeah. So I'm optimistic. I think it eventually it should happen. I think so I think the 0 round trip stuff is a good example. Okay, so if you go back to TLS, so TLS is just really everything is some version of authenticated key exchange. Although in TLS the client is not authenticated, although it could be. And 0 round trip is just less round trips to sort of set up the secure channel. So Kenny Patterson has a great paper on it. There's been Tybor's been working. Lots of good people have been working on it. And it's one of these things which is really cool from an academic perspective, which we believe and we're certain it works. And the industrial community is maybe not as keen, and there's been some debates. I think it should happen. I'm not actively engaged on that. You could ask Karthik is actively engaged on that. But essentially, if you have a good way to do any improvements on authenticated key exchange, TLS is the word for you. And it has been, actually, I think it's been overall, even though everything isn't just thrown in the standard that every academic wants, even with very good research, I think TLS has been a good example of academics integrating cutting-edge work into a web standard which has hundreds of millions of deployments and probably billions in the near future. That's a pretty big deal. And it's also using cutting-edge academic work and also just good practice in like state machine definition and whatnot improves. Really integrating that with a fair amount of corporate support into the standard. Okay, so standards are still boring. I apologize, but anyways, it's a good way to start the day. If you have any questions, you have my email somewhere. Just send me an email, and I would say that it is a really easy way. I asked Karthik. Karthik, for example, you have to choose the right standard. So Karthik spent many years investigating web services, which no one uses. But then as soon as they took the same methods developed to attack web services and use them in TLS, everyone noticed. And so, there's a lot of good research that could be done here. And it's a good way to get your work noticed if you're a young graduate student. If you feel like you have some mature work, it's a good way to both get the attention of companies and to get really massive deployment. You will get, in general, if the standards, there's lots of unsuccessful standards, but if you have the right people in the room, if you have Google and Microsoft and other interesting people in the room, and you do a pretty good job, it's a good way to get massive deployment of crypto, which is very hard to get in any other way. That being said, it's not nearly as lucrative as patenting your thing and trying to make tons of money that way, so you can make your own personal choice there. Yeah, or starting a cryptocurrency, which is, we'll see how all that goes. The attempts to, W3C is working in web payments, which is trying to integrate cryptocurrencies, particularly Ripple. We don't really know if that's going to work out, but web payments as such will probably work out, which will be good because it won't force people to be stuck with Apple or Google wallets, but have some interoperability between them. So we'll see. The blockchain community, sorry, I forgot to mention this, the blockchain community more or less copied the IETF process because Nakamoto disappeared. No one knew who he was. This guy called Gavin Anderson more or less made this thing called Bitcoin Foundation and declared himself chief scientist. And he started treating Bitcoin a little bit like his personal plaything, got some MIT money and some White House backing, and a little bit weird. And then Amir Taki, a sort of random anarchist in the UK, basically said, hey, we should copy the IETF, and so they made something called the BIP process, the Bitcoin Improvement Protocol process. which is actually just copied from the IETF, and Amir copied it from the IETF on purpose, in order to decentralize the control of Bitcoin Core away from Gavin and Bitcoin Foundation. And that was actually pretty successful, because when Gavin said, hey, Craig Wright's actually Nakamoto, and look, he signed this thing, and lost all his credibility, it was fine. Bitcoin kept going on. Improvements, are complicated, involving differing parties, miners, and everyone. SegWit's been really interesting to watch. But you can sort of see the IETF process has organically kind of evolved in Bitcoin, and we imagine as more and more hacks happen, more and more money gets involved, more and more companies get involved, things like the Enterprise Ethereum Alliance start becoming more important. Probably we're going to see, just like sort of the internet and the web, move towards more formal processes, more concern around patents and stuff. We'll probably see some of that happen in the blockchain space. Thanks.
Okay, thanks very much.